All right. So we have been discussing about active rectifier circuits, right? And in the last video we saw a circuit which was a total pole PFC rectifier, bridgeless, right? Now we will extend that concept and we would learn about something called as VSC, which stands for a voltage source converter, right? So let's move on and let's see what is this voltage source converter. So if you see, this was the circuit which we have already seen till now, which is a source, inductor, and then you have structure wherein one of the leg is switches and the other leg is diode, right? Like these devices are S1 and S2, and this is your output voltage VO followed by low. Input voltage and inductor current. So how was it operating? When you have, let's say you are using hysteresis current control mode, in that case, if approximately if this is your inductor current IL, then you have two regions essentially. One is where the inductor current is positive, the second region where you have the inductor current negative. Okay. And now if you try to draw this voltage, let me call it V1, right? Let's say this is V in, this is V1. If I try to draw V1, how does it look like? So in the positive cycle, if you just zoom into one of the area, right, and if you try to zoom in here, you would see that within this short period you would be turning current is flowing towards right direction. So by default we understand that these switches also have anti-parallel diodes connected to them. So when both the switches are open, S1 and S2 are open, in that case the current will flow through this diode D1 and will return through this diode D4, right? So current will flow through D1 and D4. So in that case the voltage V1 would be equal to VO. So if I try to draw V1, it would be equal to VO, right? VO is this level. And when I want to increase the inductor current, then I can turn on S2. D4 was anyways conducting, so if S2 is turned on, the current will flow through S2 and D4. So V1 would be equal to 0, right? So if you see, this is the zoomed version of what happens here. So overall, in this positive cycle, there are multiple times we are operating S2, turning on, off, right? So your voltage waveform V1 would look something like this, right? Something like this. So essentially switching between 0 volt and VO level. Now in the negative cycle, again you can see that in the negative cycle now inductor current is flowing in the other direction, and you would be actually utilizing switch S1, right, and turning it on and off, and thereby you would be getting, you can think over it, you would actually be getting 0. V1 can be 0 or V1 can be minus VO. Right, so essentially in this case, in the negative case, you can see VI, let's say I'm drawing, sorry, V1, right? So how does V1 look like? If your, so now your current polarity is opposite, so current is flowing in this direction, and therefore if none of the switches are operating, D2 and D3 will conduct and V1 will be equal to minus VO. And now when you want to create a zero state, or rather you want to create a zero voltage here, in that case you would turn on switch S1 and then the current will flow through D3 and S1, right? And you will have a 0 volt here. So essentially in the negative current cycle you will have V1 which is oscillating between minus VO and 0. So this is the V1 waveform that we get in this circuit which we have already seen till now, right? You can see that here the inductor current, if this is V1, this is the actual voltage which is actually oscillating, you can certainly express it, this voltage, as in Fourier series, and you can find the fundamental component, right? And you can always find other harmonics component also. So you can represent it as a Fourier series, which is a combination of multiple frequencies. How would the fundamental component look like? Fundamental component would approximately, let's say, looks like something like this. This is the fundamental component of V1, right? Let me call it V1 fundamental. So V1 fundamental and IL, if you see, are in phase. They can never go out of phase in this particular circuit. If your IL will shift, your V1 will also shift. Why? Because if this point shifts to this point, then during this period you will then have positive pulses and not negative pulses. So your zero crossing of V1 will also change, and therefore IL phasor and V1 fundamental phasor are always in phase. What does it imply? It implies that your power will always be flowing from left side to right side. Why? Because if you do multiplication of the fundamental voltage with the fundamental current, it will always be positive. So that means you always, power flow will be from left to right. Plus you cannot have leading power factor, as we have discussed. That was one of the limitation of this circuit previously, right? So to address these problems, right, so to make sure that we have a flexibility of bidirectional power flow, plus we may want to operate at different power factors, we use same circuit, almost same circuit. Only thing we do is a change, that is we replace these two diodes also by active switches. Let me draw the circuit. So you have source, inductor, and now you have one leg, you have another leg, and this is your S1. Now let me call this one as S2, S3, S4. This is VDC, and this is your resistance R, and this is inductor L, this is IL, this is V source, let me call it as VS, and this voltage, as we see, let me call it as V1. So this is nothing but a single phase voltage source converter. Why voltage source converter? Because on the DC side, it has a stiff voltage source, and therefore it is called as a voltage source converter, and popularly abbreviated for VSC. In some of the advanced courses, you may also see something else where you would replace this voltage source with a current source, and that converter is then called as current source converter. But in general, the voltage source converter is much more popular, and that is the reason that we would like to discuss about this converter in this introductory course. Maybe at some in some other courses, advanced courses, we can discuss about current source converter also. So we have not done much. We have only replaced two diodes with two switches, right, to get this circuit, which is a single phase voltage source converter. So if you see, this has four switches, right? Obviously there is a constraint between when these switches can be turned on and off. So although you have four switches, S1, S2, S3, S4, right? But as we understand, S1 and S4 cannot be on together, right? Why? Because that would create a short circuit in the DC link. Similarly, S3, S2 and S3 cannot be turned on together. So if you write all possible combinations of these switches being on and off, let's say switch S1 is on, right? If 1 is on, 4 has to be off. Let's say S2 is also on. If 2 is on, 3 has to be off, right? So essentially 1 and 2 are the only unique choices. 3 and 4 are in a way dependent. You can think it either way. But then for example, let's here see that S1, S2 are, let's say, independent. So I can write very quickly 1 0 1 0 0 1 1 1, right? These are the only 4 possible combinations, and correspondingly S3 is complementary to S4, right? So essentially you can also show this as S4 S1 is, if you use S1 and if you do a complementary NOT gate, you will get S4, and again if you take S2 and do a complementary NOT gate, and you will get S3. So let me quickly fill in this table. 0 1, okay, sorry, I think the last state I have written wrong. I've already written 1 1, so the last state is actually 0 0 instead of 1 1, right? So 1 and again 1, and here we have 0 1 0 1. Now what happens to V1 in all of these 4 situations, right? These 4 situations or 4 conditions, we actually call it as 4 states, right? These are the 4 unique states in a way. Out of these 4 states, what happens in each of these states to V1? Let us see. When S1, S2 are on, so S1 is on and S2 is on, V1 will get connected to VDC, right? So V1 is equal to VDC. When S1 and S3 are on, S1 and S3 are on, then V1 is nothing but short circuit. So V1 is 0. When S1 is off, when S2 and S4 are on, so S2 and S4 are on, again V1 is shorted through this bottom 2 switches. So again you have 0. And the last condition, when S3, S4 are on, S3, S4, then V1 is nothing but minus DC link voltage. So these are the 4 states. We would very popularly, or usually in books and other literature, we would call these 2 states as, use some other pen, as 0 states, right? Pretty easy to remember because you have 0 as V1, so you call it as 0 state. And these 2 states is called as active states. So in 0 state, if you see, inductor current is just freewheeling through some of these switches, and inductor current is not flowing through the DC link voltage or the output capacitor. But in active state, inductor current is flowing through the output capacitor. It could be charging it, it could be discharging it, but inductor current path, inductor current takes the path through VDC. So what does it mean? If you see this, essentially what I can do is, if this is the inductor current, let's say, now if I draw V1, I can use any of these, one of these 4 states, right? So either I can keep this state number, let me just randomly call them state number 1 2 3 4, right? So I can realize any states depending on which switches I turn on and off. So either I can have this kind of waveform, right? So if that is the case, if you see in this first region, I am using state number 1 and anything out of state number 2 or 3. Why? Because when I use 1, my voltage is plus. When I use 2 or 3, my voltage is 0. And I can also create this negative. And in this region, I would use state number 4 and I'll choose one of the states between 2 or 3 because both of them gives me 0 volt. I can use either of them. So this circuit certainly works at least in the same way as our previous circuit, right? Because you can get similar voltage waveform, but it does even better because now if you see this voltage waveform only depends on which switches are on and off. It does not depend on the direction of current, and therefore even if the current is not like this, even if the current is phase shifted, even if the current is phase shifted, still you can maintain this V1. And therefore, if you see now, the fundamental component of the V1 and the fundamental component of the current could be phase shifted. In fact, they could be completely out of the phase. If that happens, then the power would actually be flowing reverse, right? So in that case, what you can do is you can still have a source, have an inductor, connect this voltage source converter, and have a DC source here, let's say a battery, and you can feed power back to the grid. So both direction power flow is possible. So for example, if you have grid here, single phase grid, and if you have battery here, you can use this circuit to charge the battery, or you can use this circuit to take power from the battery and feed it to the grid. And you can do it by suitably achieving V1, right? If you can achieve V1, which gives you a fundamental voltage phase shifted, then you can feed power back also. You can absorb power, you can have reactive power, right? You can have power factor lagging, you can have power factor leading. So the limitations which we discussed about the previous circuit have been taken care of in this voltage source converter. Now this circuit is, as I told you, it's a single phase voltage source converter. It's also known as an H-bridge converter. It's also known as a full bridge converter. Okay, so these are the different names for the same circuit. Now, if you try to draw the equivalent circuit of the inverter, as I told you, the voltage waveform V1 is, if you can do a Fourier series transformation, you can find the Fourier coefficients for this, and what you would see is that, for example, left side you have grid or AC source, and here you have an inductor. And this thing you can actually represent as a series combination of different frequency components. It could be fundamental, it could be switching frequency, and it could be a lot of other components also, right? So if you neglect all the other frequencies for the time being, right, and you only draw equivalent circuit for the fundamental, so you can use superposition. This is for fundamental. And for all the higher frequencies, all the other frequencies, the circuit would look like this, because grid voltage is only fundamental. So for other frequencies, it behaves as a short circuit. So if you do this thing, superposition, let's say IL1 and IL2, where here you have a lot of other frequencies. You can say, let's say, switching frequency and other frequency sources, and the fundamental is shown in the left circuit. You can see that the left circuit is nothing but a very popular circuit which we have been looking at, which is in the basic electrical engineering courses, which is you have two sources and an inductor connected, right? So by manipulating this source magnitude and angle, you can achieve power flow in different direction, as well as you can achieve reactive power flow also in different direction, right? This is the basic two source, or rather two bus connected through an line kind of scenario, where you have two voltage sources. Let's say one is at an angle 0, other one is at an angle of delta, right? And with different magnitudes and the current flowing through the interconnected line. So with this principle, now we have understood the basic principle behind a voltage source converter. How does it operate? What is a single phase voltage source converter? Let us move further and let us see what is modulation strategy, right? And why do we need modulation strategy, and what are the different types of modulation strategy which are present for this circuit.